Hello and welcome to Fluid Mechanics. My name is Dr. Mark Taylor, lecturer in civil engineering. So this is a practical session where we're going to use some of the kit in the fluids lab to look at energy losses in pipes. So you can see the apparatus we're going to use in the fluids lab. On the left hand side we have a diagram of the Gunt HM 150.29 energy losses in piping elements rig, and that sits on top of a Gunt HM 150 base module. On the right hand side we can see the experiment set up in the fluids laboratory, and we can see the apparatus is set up with all the inlet and outlet hoses connected, and in this case we have the annulars connected to the manometer bank to allow us to measure differential pressure. So this figure shows the layout of the pipe losses rig, and it shows the dimensions between each of the fittings. The red dashed boxes show the two fittings that we're going to measure the differential pressure across, and we're going to connect them to the manometer bank. And the blue box shows the area where we're going to do some theoretical calculations to look at the change in pressure as we go through the mitered bend, through the rapid or sudden contraction and then the sudden expansion. So you can see the base module where we have point 3, a storage tank with a submersible pump, which then pumps the water up through the flow control valve at point 1. The water then passes through the pipe losses rig on top of the base module and then discharges through the outlet there and flows via a pipe into the measuring tank. So when we're passing the flow into the measuring tank, what we can do is we can then measure the volumetric flow rate into that tank. And we do that by shutting the valve, the gate valve at position 4, and then record the volume of water that is collected in a set period of time. And we do that by using the measuring tank level indicator. And once we're finished, then we need to remember to open the gate valve for the measuring tank at position 4. If we don't, we're going to flood the lab, which is not good. And then we allow the water to pass back into the storage tank, and the water then recirculates. So this figure shows the energy losses piping rig, and we can see the flow comes in at the position of the yellow arrow, then passes the first annular, and at this point we've connected this annular to the pressure gauge, and we've measured that as 0.54 bar. We then pass through the 90-degree elbow. We then go up through the sudden contraction, the sudden expansion, then we turn 90 degrees, going through the 90-degree angle. We then travel along horizontally and pass through the 90-degree bend with a small radius. Then we go down through, passing another couple of annular chambers, and then finally get into the 90-degree bend with the large radius. We then pass through another annular, a ball valve, another annular, and then we exit the rig, and the flow travels down into the catch tank or the measurement tank in the base module. So the black squares with the numbers here show the annulars that are connected to the manometer bank, and they are numbered. And number 1 and 2 are going to consider the differential pressure across the 90-degree angle at point A, and then 3 and 4 are going to consider the differential pressure across the 90-degree bend with a small radius at point B. So once we've undertaken the calculations for determining the differential pressure across positions A and B, we're then going to look at how we theoretically calculate the pressure at positions 6, 7, 8 and 9. And we're going to do this by considering the pressure at the first annular, just before the 90-degree elbow, of 0.54 bar. And then we're going to use Bernoulli's equation to calculate the pressure at position 6, 7, 8 and 9. So when you're undertaking experiments, you're going to have to produce figures showing the experimental apparatus you've used, and that's generally going to start off with a sketch. So in this case, I've just made a quick sketch showing the base unit with the pipe losses rig on top of it, and I've shown the flow from the storage tank through the rig back to the measuring tank. And I've also numbered the annulars and the connections to the manometer bank, and also highlighted that the pressure at 0.5 is taken by using the Bourdon gauge at position 5. So what I'm showing you here is a view down into the measuring tank, and here you can see the outlet hose from the pipe apparatus. You can see there's a little brass hole, and that is the connection to the level indicator. And then the larger hole is the exit to the gate valve and then to the storage tank. So to measure the volumetric flow rate, what we do is we close the valve to the storage tank at position 4, and then we look at the level indicator and we decide on a volume of water we're going to collect. In this case, we're going to collect 10 litres of water, and we then time how long it takes with a stopwatch to collect 10 litres of water. So from this we can determine the volumetric flow rate as shown in the example here. We do that by dividing the change in volume by the change in time. So the data that I collected was the first run, the change in time was 39.66 seconds, and that was to collect 10 litres of water. So that gave us a volumetric flow rate of 0.252 litres per second. I then decided to do that again just to check. So the second measurement was 39.48 seconds to collect 10 litres, and that gave us a volumetric flow rate of 0.253 litres per second. But note that we need to change that into meters cubed per second to use that in our calculations. So the pipe losses rig has a Bourdon gauge, and we can connect that to the annulars in the pipe system by using one of the hoses. And once we do that, if we have any air trapped in the pipe, we can bleed the air off using the bleed valve. But note that the measurement here is in bars. So you can see a photograph of the Bourdon gauge connected to annular 5, and we can see that the gauge is reading 0.54 bar. You can also see the bleed valve, and you can see the connection to the annular on the pipe. Note that the pipe diameter is 17 millimeters. That's because we're subtracting the wall thickness from the 20 millimeter diameter pipe. Here you can see the manometer bank, and you can see that the first 4 manometers are used to measure the differential pressure between positions 1 and 2 and 3 and 4. So just to remind you that 1 and 2 refer to the 90-degree angle, and 3 and 4 refer to the 90-degree bend with a small radius. So to allow you to do the calculations, I've given you some data here, and here you can see the various zeta values, or the coefficient of resistance, for the mitered elbow, the 90-degree angle, the 90-degree bend, the sudden expansion and the sudden contraction. I've also given you the Darcy friction factor of F, which is equal to 0.019. So there are 3 parts to this coursework. The first part is I need you to calculate the differential pressure at the 90-degree angle and the 90-degree bend. So that's position A and B. And note that I'm asking you to calculate the differential pressure, not the actual pressure, but the difference in pressure at these points across the manometers. The second part, I want you to determine the pressure loss and head loss across the 90-degree elbow at position C. And once you've done that, I want you to calculate the pressure at annular number 6. The final part, and probably the most extensive part of this coursework, is I want you to determine the pressure at annular number 7. And then I want you to determine the pressure change across the sudden contraction at position D and the sudden expansion at position E. And once you've done that, you'll be able to calculate the pressure at annular number 8 and annular number 9. So in terms of your results from the calculations, I want you to provide them in either of the following formats. If you use Word, then please PDF the file prior to submission. If you use Excel, please use multiple labelled sheets and then submit the Excel file. If you use MathCAD, then please save as a PDF document prior to submission. If you choose to use MATLAB, then use the live script file format. Or if you use Python, then use the Jupyter notebook format. You need to lay out your calculations in a clear and logical manner. Refer to each section you're working on and provide detailed annotation where required. State all data used in the beginning of your calculations and include sketches or drawings where appropriate. All the work is to be submitted on the virtual learning environment, and the submission date is also provided in the virtual learning environment. And remember, if in doubt, ask on the discussion forum. So just to finish up, I've shown you here a couple of extracts from my solutions. And I'm going to give you a couple of tips. The first one is break the problem down into a series of smaller problems and consider the difference in, for example, pressure between each point or each node or annular in the system. Don't be afraid to draw a sketch and refer to the previous tutorial questions to help guide you in how to solve the tasks. Remember, if you have questions, post them on the discussion forum, and if you have examples of your calculations, you can share them with me too, and we can discuss your problems. Good luck, and I'll look forward to your submissions.